Okay, well, we're getting to the end of the program. We have our final closing keynote speech now. It's a great pleasure for me to introduce our closing speaker. We're sort of changing tracks a little bit. For those of you who've been to our past conferences, you know we always have a climate speaker. Last year, we were all roused with a talk from Martin Hoffert from NYU. Marty always puts up these very frightening statistics about how we can't get there. And so to be more optimistic this year, and let me invite those who are coming in from the lecture to come in easily, please, and fill in the seats. You should also feel free to fill in the seats at the table as well as the seats on the side. One of the things we were interested in hearing from the Princeton study from Dr. Stephen Pacala is because they had a very interesting published articles that show that using existing technologies that it is possible for us to make headway in carbon. And so that's what our closing speech will be about today. Dr. Pacala is the Frederick Petrie Professor of the Department of Ecology and Evolutionary Biology at Princeton University. He has researched problems in a wide variety of ecological and mathematical topics, including the maintenance of biodiversity, the mathematics of scaling, ecosystem modeling, ecological statistics, et cetera, et cetera. He has recently been focused on the problems of global change with an emphasis on the biological regulation of greenhouse gases and climate. He is co-directing the Princeton Carbon Mitigation Initiative and directs the Princeton's Environmental Institute. We are very pleased to have him here today. I'm just looking around to make sure he's back from getting a drink. Okay. And with no further ado, let me introduce Dr. Stephen Pacala.
Thank you. Of course, it's delightful and a real honor to be here today. The conference has been amazing. I, too, love hybrid cars, and I love gadgets of all kinds. And so it's marvelous to be in the presence of people, some of whom get to work on gadgets every day, all the time. What I want to talk about today is solving the climate and energy problem, available technologies, and policy frameworks. The thesis of this talk is that three interdependent problems lead to the conclusion that it's time to replace the energy system we have now with another one. And these three problems are, I think there may be other problems as well, but the three that preoccupy me are the oil problem, the one we just heard about, the air pollution problem, and the climate problem. And this talk grew out of a series of exercises that started with me. I've got a floor-to-ceiling blackboard in my office. And for 2 years, every time an energy expert or an energy technology person walked in, I asked them to solve the carbon and climate problem. And they wrote down a solution. And I noticed that after the strong law of large numbers had started to converge, that all the answers were almost the same. And so it occurred to me, not only is it possible to solve this, but we already know what the answer is. And so we turned this into a game, literally a game, that's now been played all over the world, that sort of demonstrates that people converge on the problem, and that it ultimately became an article that was published in Science magazine that was, in fact, in response to an article that Marty Hoffert had written that claimed the opposite. And now I'm happy to report that if any of you have kids, the Sim City series of computer games or Sim World things where you simulate the world and things happen, well, they're actually turning this paper into a computer game now for 15-year-olds in which if you don't manage the world right, the planet cooks you or terrorists bomb New York, or quite literally, if you invest too heavily in technologies that aren't ready, your economic growth rate is too low, and aliens come and you can't defend yourself, and they turn the whole surface into slag. So anyway, I'd like to talk about what kind of energy system could we have, that is, what sort of system is the technology ready for, and what kind of an energy system do we want, and finally, what policies would give us what we want. And I want to emphasize that these three problems are interdependent, so much so that in solving at least the climate problem, you almost invariably solve the other two. It's very difficult to cook up solutions of the carbon and climate problem that don't also solve the air pollution problem and the oil problem. Going the other way isn't quite so satisfying because it's easy to cook up solutions to the oil problem that don't solve the climate problem. Usually they help, but you can actually come up with some, like liquid fuels from coal, that make things worse. But in all cases, if you want to solve the oil problem and you're interested in the air pollution problem, the technologies that you put on the ground among the constellation that you could pick include some that facilitate also and make cheaper the solution of the climate problem. I think it's really important to keep all of these things in mind because at least in my business, the sort of greenhouse warming business, it's amazing that there is no cost, there are all these cost-benefit analyses about how much we should do. But there's not a single cost-benefit analysis, at least, for instance, in the IPCC, that looks simultaneously at the oil problem, the air pollution problem, and the climate problem. Now, I want to just harp on these for a little bit longer. I'm not an economist, but this is the source for this is an economist, James Hamilton, who's at San Diego. And what this shows is the U.S. GDP growth rate. And the gray bars show the 10 major recessions that have occurred since the post-World War II period. And the right-hand side here shows his rendition of the major disruptions, the major imbalances of the supply-demand balance for imported oil that have occurred during those same periods. And there are 9 of them. And all 9 occur at the beginning of one of these recessions. All right? Now, there's an enormous amount of debate in the economics community about whether or not this recession or that recession was caused by an oil shock and how much. But the correspondence between those panels is absolutely undeniable. As a scientist, you look at that, and there really is a smoking gun there. It's also possible to cost this out. This is from the economist Richard Toll, who asked, let's suppose that there weren't any GDP growth rate penalty from this, but just the volatility. How much is it costing us? And so you can do the usual counterfactual and compute a difference. And with a 3% discount rate, you end up with a figure like $100 billion. This volatility, the dependence on oil, is in fact costing us on the order, in the U.S., of $100 billion a year. It's roughly that order. It certainly isn't $10 billion, nor is it $1 trillion. If you look at the current costs of the action in Afghanistan, actually, these are the current the costs according to the Congressional Service Report for all the enhanced security expenditures since 9/11. We have a number that's also about $100 billion a year. If you look back over the past several decades at the military involvement in the Middle East over that period, the number is of that order. All right? That's what sort of our strategic interest in that region is costing us. And I realize that this isn't the only reason we have a strategic interest in the region. But of course, we aren't also engaged in the Congo right now either, which is a highly unstable region. So this also looks to be on the order of a $100 billion a year problem. And I know no one who sort of thinks that those expenditures are going to somehow collapse catastrophically. If you look at the costs due to air pollution deaths, you can get a wide variety of figures. I like this one because this is the Bible of environmental contrarians. This is Bjorn Lomborg's The Skeptical Environmentalist. And if any of you think that, as Bjorn Lomborg writes, things are getting better and things are okay, you should read the book for the body count that's in it. I had undergraduates do this. One of the body counts in it is that Bjorn Lomborg estimates 130,000 U.S. deaths per year from air pollution. Now, that's a high number, all right? That's more than I would have estimated. But still, this is from the source, right? It's 130,000 a year, 3 million worldwide. If you use the relatively low current Bush administration figure of 2.5 million per statistical life, you get $330 billion a year. It's another big number. It's on the order, I think almost anybody would say, of $100 billion. It isn't $10 billion a year, certainly isn't $1 trillion. Now, what about the carbon and climate problem? Well, here, actually, the costs and benefits are harder to calculate. The damages from climate change, expected sort of discounted future damages from climate change in the literature vary, the estimates vary by 3 orders of magnitude. And therein lies some of the problem. We don't really know about this problem, a lot of things about this problem, and it makes it difficult. But I suspect that if somebody had the courage to put together a comprehensive analysis, then all of a sudden the 3 problems together come to a slam dunk. Now, I want to talk a little bit about the global warming problem for a couple of reasons. First of all, I think it's important to follow in Marty Hoffert's tradition and put up some scary slides. And also because I'm a global warming guy, I like to talk about it. This figure shows 2 times CO2 equilibrium warming, and it's from a group that I work with a lot at Princeton, the Geophysical Fluid Dynamics Lab. My group builds part of the Earth system model there. This is the equilibrium warming from a 4x CO2 run. And the interesting thing here is that this red color, where it gets red, that's always above 10 degrees Fahrenheit warmer per annum, and it goes up to 20. Princeton, New Jersey is about 16 degrees Fahrenheit warmer on average. Now, I don't know if you've been to Princeton, New Jersey in the summertime, but it's a lot like Houston in the summertime, and I don't want to be there if it's 16 degrees warmer. If we burn the proven reserves on the planet, the actual CO2 concentration climbs to 7x, pre-industrial CO2. Not 2x, not 4x. All the damage figures that you read typically correspond to a 2x CO2 scenario. That is something like 560 parts per million. And what we're headed for at the end of this century is 4 times pre-industrial doubling. And if we burn all the CO2 on the planet, we're heading towards 7 times the pre-industrial level. And so I don't think it's a question of if we're going to solve this problem. It's just a question of when we're going to decide to solve it. What does it cost to solve it? Well, I actually have a fair amount of knowledge of this because I co-direct a group that works with British Petroleum and the Ford Motor Company, but especially British Petroleum, where we're putting a lot of these different technologies actually on the ground and expending hundreds of millions of dollars of capital. So I know what they're actually budgeting for it. And the answer is it's currently still pretty expensive, and that's one of the reasons that you're all here assembled. Now, it depends on how you look at expensive. It's on the order, if you want to do something like carbon capture and storage, geologic storage, of $100 a ton. By the time it has to compete with other ways in which you could deploy that capital. And remember, the companies that would deploy it oftentimes make a piratical rate of return to begin with, and it has to compete against that. Now, $100 a ton is a big number, a ton of carbon now, not a ton of CO2. But it's not that much when looked at in other terms. It's $12 a barrel for crude oil, it's 25 cents a gallon for gasoline, and it's around 2 cents a kilowatt hour if the electricity is from coal. And if you look at the entire U.S. fossil energy consumption, it's on the order of $150 billion. So it's, again, this solution here, available now, and sort of the expensive version, is on the order of what we're already paying for a lot of these other problems. I want to emphasize also that the evidence for global warming, you can read contrarian websites that claim the opposite, but the scientific community is really almost unanimous. And I also want to emphasize that the scientific community is never unanimous about anything. I mean, there are Nobel Prize winners who still say that HIV does not cause AIDS, all right? But it's almost unanimous that this figure that I have up here, I think, is relatively accurate. You can divide evidence into 3 hoppers. There could, in principle, be evidence that was definitively against the view that carbon dioxide in the atmosphere from fossil burning was going to cause significant global warming. There is currently nothing out there that is definitively against. There used to be a couple of things that were problematic, like what looked like a record of no upper tropospheric warming. But those things have all gone by the wayside. And if you read on the web that these are still problems, this is old information. There are many, many things about the climate system that we still don't know. There's a huge amount of stuff in the uncertain category. And then there's an enormous amount and a growing amount which definitively makes the case that global warming is a big deal and is a problem and is real. So it's currently a shutout. There's nothing against. There's a lot for. There's a huge amount we don't know about the climate system overall. And if you want to wait, if you insist upon waiting until most of these uncertainties are cleared up, you have decided you're not going to solve this problem because the time scale over which we're emptying that middle box is long. It's decades long, and the problem needs to be handled before that. It's also important to understand that the evidence for global warming does not come from any one source. The divide and conquer strategy is one that's employed by the other side, the skeptical side, all the time. It comes from the record of climate change in the past, about which we know an increasing amount. It comes from both mathematical theory, physical theory, and models, and climate models. And it comes from current records, the current record of warming. All these things are in agreement, all right? And it's possible to poke holes at any one of these pieces of evidence, for instance, to say that the models are still not perfect, and that's true. But it's when you look at the totality of the evidence that the case becomes compelling. I want to spend a little bit of time now about monsters behind the door. And I've got some new results here that aren't published yet that I thought you ought to know about. There's some that you've heard about and some that you haven't. Usually when we talk about global warming, we think about the problem being, you know, the slow, steady rise in sea level and the creep up of the temperature that causes increased heat-related deaths and damages to ecosystems and changes in the distribution of water around the planet. But there are some relatively rapid and catastrophic changes that are increasingly worrisome. And I've got 4 here, some of which you've seen before. There's the instability of the thermohaline circulation. A lot of you probably saw the movie The Day After Tomorrow, which was a highly fictionalized version of what goes on here. This is really easy to understand. It turns out that if you look at the oceans, Antarctica is squatting on the bottom. And there's only one good, clear passage of deep water into very high latitudes, and it's right there. So there's a narrow strait here. Water can't get through, but the water is 10,000 feet deep there, and it's nice and wide. And what happens when water gets cold up there is that its density goes up, and it wants to sink. And when it sinks, water has to come from somewhere, and it comes along the surface to fill up the drain that's been put in there. And as it comes up from the south to the north along the surface, water evaporates from it, and the salt concentration increases because the salt gets left behind, so it becomes saltier. And the salty water is also dense, and that increases the drain and increases the sinking of the water there. So there's a great big drain just because of the arrangement of the continents right there. And that drain is caused by the coldness, which increases the density of the water, and the saltiness, which is caused by the evaporation as it moves to the north. And that sets up this whole pattern of deep sea oceanic circulation, that force, that drain up there. Now, global warming stops the drain because it changes the temperature gradient, and it also melts the glaciers that are up here and freshens the water up there. And in models, that turns off like that. It's a bistable system. And this is a huge heat pump that makes the North Temperate Zone sort of habitable. And in the past, this has changed. And when it turns off, we can't tell how fast it does because, well, at very high resolution, because the Greenland ice core has some problems in it. But we know it takes less than 10 years to switch when it switches. It probably only takes a year. It may only be a few weeks. All right? But this is the kind of thing that almost without warning in the past has flipped on and flipped off. And models say that this starts to happen when we exceed a doubling of the pre-industrial concentration of CO2. This is particularly timely for a city located on the Gulf right now. This is a hurricane intensity figure. Notice category 5s are here. And this comes from a study by Knudsen and Telja that was just published in 2004. This is a distribution after 80 more years of business as usual CO2 emissions. And this is the distribution of storms that were fed this system. This is one of many such studies that show that global warming exacerbates hurricanes. Now, usually the effect is written down as though it's pretty small. But it's important to understand that that is not correct. What happens is, instead of the distribution changing shape slightly, what happens is it shifts a bit to the left so that always this tail, this is the low pressure, high wind speed storms, becomes much thicker. The area under that tail, the frequency of bad storms, the killer storms, the category 5 storms, goes up in this figure by more than a factor of 10. And that's the problem. The average intensity doesn't increase very much, but the tail of extreme storms increases enormously. Kerry Emmanuel, who is the current sort of hurricane guru, a guy at MIT, has on his website that you can't attribute Hurricane Katrina to global warming. But his own private calculations give it an 80% chance that it would have been a Category 3 without the extra CO2 in the atmosphere. All right, so that the levees broke, of course, because we exceeded a Category 3, and this is the problem. So in a world post-2050, hurricane models that are increasingly sophisticated make 200-mile-an-hour storms not very uncommon. All right, and that's a problem, obviously. This is I think the last one I'll probably talk about. This result is not yet published, and it's something that's come out of our model. The drought in the Sahel in the late 20th century is shown by the black line. The red line is the prediction of our Earth system model. It's almost a perfect picture of the Sahel drought. And this shows the actual drought here. And so this is rainfall on this axis. And this shows the drought that is produced by two versions of our model. When we run that out, this drought, which ceases for a little while, picks up and becomes much, much worse during this coming century. Now, the Sahel drought has already killed, depending on who you listen to, between 1 and 10 million people. So it's an event like a major war. All right? So this is a big deal. And in our model, at least, this is caused, the Sahel drought and the future Sahel drought, is caused by global warming. It's caused by CO2 in the atmosphere. There's a disruption in the eastern tropical Pacific's convection that has a teleconnection to this area. It's something you can trace. And what's most important is that it's something that you could actually verify with satellite measurements and whatnot. And the reason this is a big deal, at least for the people in industry that I talk to, is that they're afraid of the liability risk that this increasing ability to attribute specific events to actions represents. All right? And so anyway, that's another problem. And finally, there's some new work on ice sheet instability, but I'm going to get way out of time here if I don't move on. Okay, so the middle part of this talk is a synopsis of a paper that came out in August 2004 that was a reaction to a paper that Marty Hoffert and a whole bunch of other people had published saying that we lacked the technology to solve the carbon and climate and the rest of these problems. And we said, yeah, you can. All right. Now, this doesn't mean that revolutionary technologies aren't needed. And indeed, I think the best way to get them is to start to solve the problem with the technologies we have in hand. That's the way to get the investment in R&D and the interest in this problem necessary to get the revolutions. Okay, so the game is as follows. These are billions of metric tons of carbon. That is emissions per year, 1955, 2005. This is the historic record of historical emissions. We had to come up with a business as usual, what's going to happen in the future. And so we just said, let's just draw a straight line. All right, it's going up about 1.5% per year. That causes things to double if this pattern continues over the next 50 years. All right, so that's the current path. When we look at our models, we say, what do we need to do to avoid the doubling that leads to the monsters behind the door in our models? And the answer is, to avoid that doubling, we need to freeze emissions for the next 50 years. So we would have to cut out a triangle that goes from 0 today to 7 billion metric tons of avoided emissions 50 years from now. All right? That's what we need to cut out if we're going to solve this problem. We call that the Stabilization Triangle. Now, there are other, of course, paths that this thing could take. But if you look at the literature on this scenarios business, this falls right in the middle of them. And I think it's because whenever you build a complicated scenario, what's going to happen in the future, you sense check it against whether or not it looks like the last 30 years. And if it doesn't, you throw it away, right? So that's what I think is going on here. Now, this isn't done at 2055. If you want to keep things at less than the doubling, then the emissions per year would have to ramp down and eventually match declining ocean sink. But that's the job for the next half of the century, and for that we are going to need revolutionary technologies, all right? But nonetheless, to get there, if you don't do anything and climb to here and then stabilize, this leads to a more than tripling of the pre-industrial CO2, and we're right in the middle of the red zone for all the bad things that happen with climate change, all right? So if you want to avoid the tripling, the dangerous tripling, then basically you have to freeze things for the next 50 years, and then you have to have revolutionary technologies available to move on beyond that. It's also important, I think, to act now. Another case can be made to act now, that can be made for acting now. It is shown here. This cylinder shows all of the CO2 that's ever been emitted in the last 250 years, all right, since the beginning of the Industrial Revolution from fossil energy. And this cylinder, this is from David Hawkins at NRDC. This cylinder shows the current commitments, the total lifetime emissions from the power plants that are currently in the World Energy Outlook that are going to be built by 2030. So the lifetime emissions embedded in those plants that are on the books right now and that are forecasted, they would emit almost as much CO2, sort of 2/3 the amount that we've emitted thus far, just in building those things. So the design of those plants is absolutely critical, and it's something we're going to have to deal with in the next couple decades. I also want to point out, this is Marty Hoffert's primary criticism of our work, that we assumed the continuation of the current trajectory of emissions, a growth of about 1.5% per year. But the economy, of course, grows much faster than that. The economy, the global GDP, grows at 3% per year. And so Marty says, well, gee, that's an efficiency gain that's already embedded in the system. And this gigantic virtual triangle that you're saying somehow is going to be magically created, isn't that going to compete with your existing technology? Isn't that caused by, isn't the fact that for the last 30 years the economy has grown at 3%, while CO2 emissions have only grown at 1.5%, isn't that caused by increased energy efficiency? And the answer is yes, but only in the most strict economic terms. And I actually don't think it competes at all. This is a busy slide, but if you're a geek, you'll love it. They have gross domestic product on this axis, and we have CO2 emissions on this axis. Each vector is the time trajectory, 25-year time trajectory for a country. The base of the arrow is at 25 years ago, and the head is currently. And you see the U.S. is stuck out here, pointing the way. These lines correspond to various ratios between GDP growth and CO2 emissions growth. The important thing here is that there's a lot of structure here. Some economies are developing in such a way that they're bending over this way. Others are following what looks like this historic trajectory, but all of them are bending over. All of them bend as GDP grows. And you can analyze these data very carefully to ask, why is it that this happens? Why is it that this gap continues to open between GDP and energy? And the answer is the growth of the service economy. All right? Almost all of it is the growth of the service economy. It's not the increased efficiency of steel production. It's not the increased efficiency of home heating. It's not all of the things that we would do to solve the carbon and climate and oil and air pollution problems. It's each other. It's everybody in the world is giving each other a massage and then sending their taxes to an accountant and all that sort of thing. It's all the service economy that's growing. Okay, so now we want to ask, if we have to fill this stabilization triangle, which is over a 50-year time frame, a sensible definition of what it means to solve this problem. It doesn't really solve it. It just gives our descendants the capacity to keep solving it. But if we don't do this, we certainly haven't solved the problem, all right? It's a sensible time horizon for the people in this room, for students at colleges, and it's also sensible from the perspective of the lifetime of capital stock, long-lived stock like power plants. And you want to ask, is there any technology that's big enough to fill that whole stabilization triangle? And I don't think there is. I don't think there's one that you could scale up enough even to do half of it. Marty Hoffert's paper I likened to a kung fu movie, where in a kung fu movie, the good guy is always standing there. There's like 50 bad guys, and they come at him one by one to get beat up. You ever notice that? That's exactly what Marty did. He said, look, we have 30 terawatts of energy that we have to do. Could wind do it all? No. Could biomass do it all? No. Could nuclear do it all? No. Never ask what happens if they gang up on them, all right? Okay, so what we're doing here is we're going to divide this into 7 equal wedges. Each wedge rises from zero avoided emissions today to 1 gigaton, 1 billion metric tons 50 years from now. And we want to ask which technologies are already deployed in the marketplace that are big enough to fill at least one of those wedges. All right? It's like high-stakes poker. If you want to play, you got to be able to fill a wedge. There are all kinds of things like biodiesel or something that may or may not be in here because I don't think they can be scaled up to do the job. I'm only going to be looking at technologies already deployed in the marketplace. These are not technologies that are in a benchtop or in a demonstration project or something like that. These are things that are already at a full industrial scale. It doesn't include any of the revolutions that I love. This is a tokamak that was at Princeton and has now been replaced by a much smaller one. I hope fusion works someday. I think it's cool. Artificial photosynthesis, whoever the talk on photochemical reactions, I tell every Princeton undergraduate in my non-major science course, which is huge, that this is the best job in the world, is to work on artificial photosynthesis, on photochemical reactions that take CO2 out of the air. Because every day you get to go to work, if you succeed, you both save the planet and you become the richest person in it. All right? I just think that's wonderful. Photosynthesis is an incredibly inefficient process. We have terrible, weak, pathetic biological materials that lose almost all the energy in an electron transport cascade because they can't take the energy of a fluorescing electron. So you capture only a teeny bit of the energy. And in a Rube Goldberg device that is proof of unintelligent design. Any engineer would design something better than this. Okay. So I want to fill the triangle with technologies already in the marketplace at an industrial scale. And I'm going to go through a few of those. Now, I've got a whole bunch of different wedges. Wedges of efficiency, wedges of decarbonized electricity, wedges of decarbonized fuels, fuels displacement by low-carbon electricity, and I've got natural sinks. All of them, except for the natural sinks, would contribute to solutions of all three problems that I talked about, the oil problem, the air pollution problem, and the climate change problem. I'm not going to talk much about efficiency and conservation, and the reason is that much of this conference has been about efficiency and conservation. Just heard some interesting talks about hybrid vehicles, and you know, I've got one example of what a wedge would be if you were going to do it with fuel efficiency in fossil fuel burning automobiles. The effort needed by 2055 for one wedge would be 2 billion cars that were getting 60 miles per gallon instead of a 30 mile per gallon, say, business as usual. That gives you 1 billion metric tons of savings by 2055. So you see how small a piece of this problem the transportation sector really is, all right? Because this is a huge thing, and you're only solving 15% of that, 15% of it. Right now, there's about 500 million cars, right? So it's not unreasonable that there will be 2 billion in 2055. And it's also not unreasonable to think that if we did nothing, they'd be 30 miles per gallon, and we know that we could get them by then to 60. So that's a wedge. And we have lots and lots of examples in the science paper and in the very, very long online section on this. So I'm not going to talk any more about efficiency and conservation. For nuclear electricity, the effort needed for one wedge would be to roughly triple the nuclear electricity currently deployed with about the same capacity factor. That is, we need roughly to build 700 gigawatts of nuclear power plants to build one wedge. And of course, this is possible. The rate of nuclear power plant construction for a 15-year period in the late 20th century has exceeded the pace you'd need to do to get to one wedge. Now, of course, there are all kinds of other problems that you might also develop if you tried to solve too much of this problem with nuclear electricity. But make no mistake, this is feasible. Point's already been made. We're the Saudi Arabia of coal. I want to have a few facts here about coal because I think it's really important to understand from a U.S. perspective, at least, what's going on here. That's U.S. coal reserves. That's a bunch of other countries. We are the Saudi Arabia of coal. This is a picture from the Department of Energy about our coal reserves. Our coal reserves in this country are like 10 times the oil reserves in the rest of the planet. This is a big deal. We have so much coal in this country that we could make use of. I think everybody knows the information that's on this slide, but it's important for everybody to be on the same page also. you can take coal now, and there are lots of different ways to use coal that aren't the traditional uses of coal in power plants, where you combust it and boil water and make steam and run power plants. One route is to partially burn the coal, partially combust it to carbon monoxide, and you can burn it in a turbine. And that's great, because that reduces the air pollution that the coal plant would otherwise do. And this is a big deal and everything. But it's also, of course, possible to add water to the carbon monoxide in a water-gas shift reaction and make a mix of carbon monoxide, hydrogen, water, and CO2. All right? And so the oxygen comes off the H2O and gets on the CO, and you make some CO2. So this is a partial reaction. You've let the reaction go until the CO to H ratio in this mix hits a sweet spot, and then you can send it to a syngas reactor and make liquid fuels. And those liquid fuels will work in a car, and they'll displace imported oil. The problem is that there's a lot of leftover CO2, and if you vent it to the atmosphere, that car, when it burns the gasoline, it emits only the same CO2 that the gasoline would have emitted, but there's an equal amount of CO2 that's vented into the atmosphere at the coal plant, at the plant that makes the synfuels. So if you use this technology, which the governor of Montana has suggested that we do, you actually will make the CO2 emissions from the transportation sector twice as bad as they are today. All right. However, if you just keep this shift reaction going, eventually it goes entirely to hydrogen and CO2. And when it's at hydrogen and CO2, you can sell the hydrogen to hydrogen cars, which I also think is a long way off. Or you can burn it in a turbine for stationary power. And, of course, the thing you do with the CO2, if you don't want it to go to the atmosphere, is you have to put it someplace. And the obvious thing to do is to stick it in a geologic reservoir. Now, this business of using hydrogen derived from fossil fuel with geologic sequestration, if you listen to the sort of federal government's rhetoric, is a long way off. Future gen is something we're going to do at some future time. But the group we work with, after we worked with them very hard about this, we're building a plant right now that does this. It's a 350 megawatt plant in Peterhead. This is the only land in the figure. This is the northern tip of Scotland. And we're steam reforming natural gas, swapping the turbines out in a 350 megawatt power station. We're burning the hydrogen in turbines and producing electricity. And we're sending the CO2 that's left over out in an existing acid-compatible pipeline to an offshore platform whose decommissioning costs we can now avoid. All right? We're injecting the CO2 into the ground in this Miller field, producing extra oil and bringing that on, and the whole thing is economical, all right, given the existing peculiar subsidy structure associated with decommissioning platforms and whatnot. So this is definitely doable, and there's more on the way. And the next ones won't use natural gas, but that's all I want to say about that. There's also a lot of experience now with geologic sequestration. This is a project that BP started in the middle of the Sahara a couple of years ago, and it injects 1 million tons of CO2 a year into a deep aquifer that's beneath a natural gas field. It's a natural gas field that has about 12% CO2 in it, and because of the economics of transport, it makes sense to strip the CO2 out of the natural gas before you sell it, before you move it. The normal thing to have done would have been to have put the CO2 into the atmosphere, but because of environmental concerns, it's being re-injected here. This is one of several now facilities operating around the world. So a lot is known about this geologic sequestration, in addition to what has been learned from enhanced oil recovery. Now, the effort needed for one wedge of this sort of thing, if you built power plants that had carbon capture and storage, so that you didn't emit the carbon to the atmosphere, and say you burned hydrogen in turbines, you could also scrub the flue gas in principle, is roughly the same as for the nuclear plants. About 800 gigawatts of coal power plants would have to be built in this form instead of in the traditional form. And that gives you, in 50 years, a wedge. Coal-based synfuels, same sort of thing. You could make synfuels and capture the CO2 that would have been emitted to the atmosphere. Remember when you make synthetic transport fuels from coal, you emit half the CO2 at the plant and half of it in the car. Well, the CO2 at the plant is captured, and you could stick it into geologic storage. If you did that in plants producing 34 million barrels of synfuels per day, then that gives you an entire wedge. By comparison, the Sahel plant in South Africa produces 165,000 to 180,000 barrels a day. So this is like 100 to 150 Sahel plants worth. Incidentally, if we produced 50 of those Sahel plants in the United States using, well, the upgraded technology, the new stuff with geologic sequestration, we wouldn't import any oil at all. All right? 50 plants. Fossil fuel-based hydrogen with carbon capture and storage, same sort of thing. Effort needed for a wedge is hydrogen instead of gasoline or diesel in 2 billion 60 miles per gallon of vehicles. How much carbon storage do you need? We've got a lot of experience, as I said, with these. The effort needed for one wedge is 100 times the current CO2 injection rate, almost all of it in Texas here in the Permian Basin for EOR, for enhanced oil recovery. So this is a big scale-up, but it's not an unprecedented scale-up. It's a factor of 100 scale-up. It's 3,500 of those Algerian projects, or for those of you who know this sort of thing, this picture is from a North Sea injection facility run by the Norwegian company Statoil. It's 3,500 of those operating at 1 million tons of CO2 per year. There's some problems with geologic sequestration, but I'm not going to go into them. All right, they have to do with, the biggest problem has to do with leakage from old wells. There are old wells all over the place. In the Permian Basin alone, there are 2 million old wells that have been capped with various kinds of technology since the 1800s. A lot of these you don't even know where they are, and you don't want the CO2 to escape through the old wells. We've got a big research project going at Princeton about this. Many others do too. I think a lot of you come from institutions with comparable programs. We're drilling out old wells, getting side cores, and taking a look at the concrete. We're doing high-pressure experiments. We've got logs of all the old wells. These are the 300,000 old wells in the Alberta Basin. They go back to 1880. This is a problem that can be managed. We don't have to deploy in suspect areas for a long, long time, and it's possible to learn as we go. I think this problem is solvable, but it's one that needs to be taken very, very seriously. A wedge of wind electricity is 2 million 1-megawatt wind turbines that are displacing coal power. Today, I think the number is closer to 50,000 megawatts deployed, but some of you know that better than I do. Obviously, you wouldn't do 1-megawatt wind turbines anymore. They'd be 1.5 or 2, so you'd need half as many, so 1 million 2-megawatt wind turbines. This is a big scale up, but over 50 years, the current growth rate would take you there. If you went to wind hydrogen, it's actually twice as bad. The inefficiencies of producing hydrogen mean you need twice as many to make one wedge. Solar electricity, it's a lot further to go, but it's really cool if you can get there because you only need about 2 square meters per person to get a whole wedge in 2055. There's a long way to go with it because we don't have nearly as much. I should also say, because you people know a lot about this sort of thing, when I'm talking about a wedge of wind electricity that's a peaking thing, an intermittent source, displacing coal power, which is base load, I've got a capacity of 3 that I'm building in. So this is 3 times the megawattage of coal plants that it's displacing. So if I have to displace 800 gigawatts of coal, I'm building 2,400 megawatts, or gigawatts rather, of wind to handle the peaking. Biofuels, you'd need 2 billion 60 miles per hour, or miles per gallon cars running on biofuels. This requires, using current technology, about 250 million hectares of land and high-yield crops, which is 1/6 of the world cropland, and a little bit more. Okay? I've gotten hand signals. Yeah, still got 15 minutes or so. 250 million hectares is roughly U.S. cropland. All right, so this is a big deal. It competes with cropland for a food-hungry world, but it's also feasible in principle to do this sort of thing. Natural stocks, this is the only one that doesn't help solve the oil problem and doesn't help solve the air pollution problem. If you eliminated all tropical deforestation by 2055 and rehabilitated 400 million hectares of temperate or 300 million hectares of tropical forest, which you could do, you get an entire wedge. You really can't get much more out of the biosphere than this. You might, by stretching it, get something like a seventh of the problem, but it's always going to be a minor player. It's also at least in principle possible to get a wedge out of soil conservation. When soils are turned over, the decomposition rate goes up, and that causes carbon to leave the soils. Since agriculture, over the last 2 centuries, agriculture has removed 55 billion tons of carbon from agricultural soils. Current practices like no-till agriculture, where you drill the seeds into the ground, reverses the carbon losses. And it's currently practiced on 110 million of the 1,600 million hectares of land, of agricultural land. And if you simply extended it to all the agricultural land, which can be done at very low cost, then in fact you reverse the losses and you'd get about a wedge out of that. Okay, so if you look at the options as a whole, I've shown you some of them. In the paper, we outline about 15, and there are others that we could add also. Several of these options that are deployed already at an industrial scale could supply 2, and a couple could even supply 3 wedges at a stretch, all right? And so that there is more than enough technology, at least in principle, to fill each one of these things, and each one at $100 a ton or less. And so we have an oil problem that's a $100 billion a year problem for the oil price shocks and $100 billion a year for the instability currently in the Middle East. We have an air pollution problem that's a $100 billion a year problem. This is just in the United States. And we have a climate problem that, if we're paying $100 a ton, is a $100 billion a year problem to solve. And so how would we get this done? And I also think that we already know, that economists already know what you would have to do to get this job done. If you decided to do it, what do you have to do? Well, you have to put a price on carbon. Everybody knows that. We know what to do. Any economist just about will tell you that we need some sort of cap and trade option like McCain-Lieberman. But this is not, at this point, in my view, an economics problem at all. I think you can sort of do the math and say, yeah, this is probably something we ought to do. This is a political problem. How do you actually get the deal? How do you get the job done? And there, I think, the policy options really, really play out. There are all kinds of ideas on the table. There are revenue-generating taxes that go nowhere, just big carbon taxes. They go nowhere. Tierney, the conservative columnist in the New York Times, who's a Julian Simon disciple, on October 3rd, surprised the heck out of me by proposing a 50-cent per gallon gasoline tax, all right, that would then be rebated to consumers in personal retirement accounts in order to alleviate Social Security. And he actually got it by Grover Norquist. Grover Norquist wrote a little thing saying that he supported this idea. I was just amazed by that. A guaranteed floor price for oil, for imported oil, is another possibility. Oil is currently high enough that making synfuels from coal and other sources is something that would be economical. But the fear about the volatility in the oil price makes it difficult for private industry to invest the capital in doing that, because it's a huge gamble. And also there's a game theory at work here. The OPEC nations, if faced with a huge investment by the rest of the world in displacing oil, could well, by private enterprise, could decide, look, let's overproduce for a little while and drive the price down, all right? Drive them all under and make them never do it again. And so there's a lot of fear in private enterprise when you have to put $1 billion on the line for a plan about what the future price for oil is. A guaranteed floor price would probably cost consumers nothing and would facilitate investment in capital for alternatives. There's obviously the possibility of technological subsidy. There are portfolio standards. There are a whole lot of ideas out there that make the politics politically feasible, maybe. But I don't think that most economists would just call most of these ideas, this is sort of bad economics, but maybe good politics. So the conclusions are, What I think we need more than anything else is a national policy designed to solve the oil problem, the air pollution problem, and the climate problem. These are synergistic problems that can all be solved in one fell swoop if there is a dedicated effort that takes decades, that's decades in length. We already possess the cost-effective technologies for the next 50 years if costs are seen in the context of what we are already paying as a society. The solution will only get cheaper as investment elicits industrial R&D, and especially when you people invent revolutionary alternatives that really drive the costs down. So that's all I have for you today, and I'd be happy to take questions.
Very good. Okay, we'll take some questions from the floor. Please use the microphone because we're simulcasting, and otherwise we have to edit out your question.
Yeah, can you hear me okay? Is it on? One of the questions or points you brought up is a lot of the things that we're doing would reduce the carbon dioxide, and but there's still burning going on. And the question I have is that what would it do to the oxygen supply of the world? And that could we reduce the oxygen level from its regular 20% to a lower number?
Well, you can reduce the oxygen to a lower number. In fact,
what would be the consequences
well,
of that?
I'll get to that in just a second. We work on, we use fluctuations in the oxygen supply in the atmosphere to monitor the biosphere and to monitor combustion right now. But whereas CO2 is 300 parts per million in the atmosphere, that is 0.03%, right? Oxygen in the atmosphere is about 20% of the atmosphere. So there's this huge amount of oxygen in the atmosphere, but only a tiny amount of CO2. And now when you burn, you take carbon and you add an oxygen molecule to it. And so there's a stoichiometric equivalence there, all right? And so a big change in CO2, like a doubling, is a tiny perturbation of oxygen. All right. So the answer is it would do a little bit to oxygen, but not enough to affect life as we know it. In fact, that inefficient photosynthesis system that I said was proof of unintelligent design, one of the things that's really fascinating about the geologic history of the Earth is that of course, created the oxygen in the atmosphere. The development of that photosynthetic system all of a sudden released oxygen to the atmosphere and poisoned everything in the planet. It killed almost everything on the planet about 2 billion years ago, and in fact drove everything underground. We're all descended from hyperthermophiles from deep in the earth near geologic hydrothermal vents because everything killed itself off. And the oxygen kept creeping up in the atmosphere until it stopped just short of the limit for spontaneous combustion. All right? We're actually perched on a precipice where oxygen in the atmosphere is both toxic and dangerous. Every cell in your body is a colony of several different species of bacteria forced to live together to try to keep the oxygen from killing them. All right? So we could afford to lose a little bit of oxygen. All right? Yes?
In your conclusions, you use the term, we need a national policy. How will a national policy solve a world problem?
Well, I think that right now, a good argument can be made that the rest of the world has decided to solve the carbon and climate problem. And it's the United States that is currently dragging its feet on this problem. And I think that if the United States exerted leadership, and that leadership would first take the form of a national policy, then I think that the world problem would also be solved, because I think the world's ready to be led on this. I know there's a lot of concern about China and India and some of the developing economies. But the fact of the matter is that those economies don't emit that much until they get pretty rich. And when they get pretty rich, all of a sudden they can pay. And they've already shown a willingness to do it. I know for a fact that China is interested in building polygeneration plants from coal that emit nothing. And they're worried about the air pollution problem primarily, but they're worried about the oil security problem also. And as they become richer, they're going to also worry about the CO2 problem.
I just want to make clear up front that I'm not a climate change skeptic, so I accept much of the premises regarding the warming scenarios and the data on that. But I am a skeptic of your master of wedges theory that you put forward to resolve some of this stuff, having spent most of my career in the last 15 years developing lots of those technologies within those wedge pieces. And I think some of your underlying assumptions are highly suspect. You know, when you start talking about where a wind turbine ought to be on its sizing, I mean, that's completely relevant to the siting of the wind turbine plants. And there's no reason to expect that wind turbines will ever be over 1 megawatt if they're on the side of a mountain ridge, for example, and that's the best available wind. So it's, you know, the devil is in the details, you know, on each and every one of your wedges, and I think you're missing a great deal of detail. I'm not at all clear where you're going with the use of coal, so I'd like you to elaborate on that now, you know, specifically on coal to liquids, which sort of has an imminent future. Let's say coal to liquids with sequestration. Are you for that or are you against that? And if you're against that, where do you see this big stockpile of coal going to? And for the record, I'd like to understand both qualitatively and quantitatively what exactly a piratical rate of return is.
Piratical rate of return. I mean, I'm amazed at the rate of return that some of the people I deal with. I note that 28% per annum is a piratical rate of return, in my view. All right, that's the number I have in mind. But I think it's great. I think free enterprise is great. I think it's marvelous that people can make money, and and it's important for the pensions of little old ladies and everything else. So I don't want to argue about the piratical rate of return, but I will address the other points with some seriousness. The first thing to understand is that the purpose of the wedges paper was not to pick favorites. All we wanted to do was to counter the claim that we lack the technology to get started. This was Secretary Abrahams, at the time Secretary of Energy Abrahams' stump speech. His standard speech was that we need a revolution as revolutionary as electricity was in the 19th century to get started. All right? And also this paper that came out in Science that, in my view, was sort of a grant proposal masquerading as an energy analysis, made exactly the same point. All right? And so our purpose was to show that one could do this and that we have enough technology to get started. But we did not pick favorites. So when it comes to wind power, what I'd like to ask you is, do you think it would be impossible to build a gigaton of wind capacity in 50 years' time? Using offshore wind, onshore wind, do you think that that's an inappropriate wedge, or could you get to a gigaton? Yes.
I think the answer is in the rest of the work that this conference did. It's really a transmission access siting issue, not a technology issue in terms of wind as a prime.
But do you think we could get there?
Relative to our ability to bring that wind online and keep load stability, you know, as part of a national or, you know, international plans, if you're doing this country, it's relative to grid access, and that's what can get us there. If it's not economically feasible to move the wind from the windy places where it's a least cost resource, then we will not get there.
But okay, so I guess, my assertion is only that with the appropriate policy to elicit that gigaton of wind, you could get the gigaton of wind. And then it goes into our wedges, then it gets included in our wedges game. All right.
I guess the point I was making is, you know, the devil is in the detail in all this, and the detail should not be underestimated in terms of the time span assertions that you're making on all of this. That's because your triangle is time span dependent. On the coal to liquids, for example, my understanding is all of that needs to be burned in diesel reciprocating engines. So what's the conversion of the fleet? Right now, that's all agricultural tractors and country trucks. So if you start talking about fleets on the magnitude of 2 billion, I mean, I don't know that Houston can handle another 1 million cars on its infrastructure capacity highways today. So there's a lot of detail in there, is what I'm asserting.
First of all, in the paper, and especially in the 50,000 word online section, there's a lot more of the detail that you seek. But I think that this is a problem. I know that when I look at the energy analyses, and in particular the integrated assessments, for instance, as part of the IPCC, where all of this information is embedded, the problem is that there's too much detail. And it's very, very difficult to envision solutions to this problem, and especially for somebody who's trying to come into this problem for the first time, to develop a way to envision solutions to the problem. And in my view, that's been one of the chief impediments. Now, when it comes to the problem of coal to liquids is on there simply because it would be in principle possible to sequester the carbon, and it would in principle be possible to build that many coal to liquids plants. My own view is that maybe this isn't the right solution. All right, it is in fact possible, of course, to run a constant velocity diesel engine in an extreme hybrid and have something that's very fuel efficient and produces very little air pollution. And you can do this with Fischer-Tropsch liquids. You can do this with dimethyl ether. You can do this with any number of things that you can make out of coal. So it's possible to build an environmentally friendly, carbonaceous liquid fuel out of coal and sequester the carbon, and that's why it's on the list. But it's also possible, of course, to use coal and to produce CO2-free electricity if you can sequester it. Now, the sequestration job is enormous. I don't believe we're ever going to fill more than one or two of these wedges with geologic sequestration. A back-of-the-envelope calculation that is useful is that if we sequestered all of the CO2 currently emitted by the United States into the coterminous United States as a supercritical fluid at the usual depth, at roughly 1,000 meters, then the entire surface of the country would jack up by about 1 millimeter per year. All right? Yeah, that's right. Helps combat sea level rise. All right? But you don't need to be a scientist to realize that there are likely to be some problems with that. All right? And so even when I talk to oil company executives who are likely to make a lot of money on this, they never put more than a wedge or two of geologic sequestration in. All right. So I think this is an important interim technology. I think it's really important for bringing an important constituency to the table. I think it's great bridging technology, but it's not the full answer. All right.
I know there are a number of combinations to the solutions that are the options you put forward, but what is your best guess on the impact of the GDP from deploying those options? Because I gather a lot of the opposition to this is concerned about the impact on projected U.S. growth rates, and so I wanted to, assuming that we do some combination or some reasonable set of the things that you're suggesting, what is your best guess, if any, about the impact on that?
I'm not an economist. I want to emphasize that. So all I can do is tell you what I have read that economists have done. All right? And the answer is that about 20 years ago, a whole bunch of economics models that were pretty simple were used to forecast what the effect would be for solving this problem. And the answer was globally 0.5 to 1% of GDP, something like that. That is because of the miracle of exponential growth, 1 year in which global GDP was 2%, not 3%, and then it gets to be 3% from then on. All right, that's the cost, one-time total cost, right? Because everything grows exponentially. Now, that's a big number, but we're also paying an enormous amount for the current energy system we have, and I think that needs to be brought into the equation. The other thing I want to say is that in the intervening 20 years, there has been an enormous effort to build ever more complicated integrated assessment models that forecast the economy of the world in all of its sectors out 100 years and more. And these things continue to show that we get on the order of 1% of GDP. We are not going to solve this problem, and we're not going to know the answer by more economic analysis. The answer is, our best guess is that it's about 1% of GDP to solve this problem. And it's not until we start to deploy in earnest that we're going to find out if you people are smart enough to really buy the cost down a lot, or whether or not this thing is a lot more intransigent than it looks and the costs are a little higher. If the costs turn out to be a little higher, we'll probably abandon it. But we'll never know unless we experiment with the system. All right.
It's interesting that you're backing up a little bit from the CO2 argument, and I worry a lot about the CO2 too, because I think that NIMBY never saw anything like CO2 clouds under your basement. I mean, Bhopal in your basement while you're sleeping is a pretty scary thought, and that's how much CO2 we're talking about here. But what I see coming out of the CO2 argument is that a lot of coal companies and a lot of people who are basically looking for, if not a silver bullet, something like that, are really latching onto that and saying, well, this is the solution. We're going to burn a lot more coal. We're going to bury the CO2, and we're going to use it in both transportation and electricity. So even though I actually agree with you, 90% on a lot of what you're saying in terms of the fact that we can do it. I think we don't need a revolution. We can do it, and if we revolutionize things, well, they'll be in their own good time. There's plenty of reason to do it. I'm a little afraid that basically the message is really that we'll pick our favorite wedges, and those are the ones we'll just do. You mentioned Montana, and I'm sure Senator Byrd's interested. I mean, that's more constituency than I'll ever see, in 100 lifetimes already. So I really visualize this as kind of going down the same pathways, more of the same, but a different kind of same.
Yeah, I mean, this problem is big enough that there are risks all over the place, no matter what we do. The business about geologic sequestration, it is possible. It's certainly the case that CO2 put below ground, that finds, especially finds an old well, all right, and comes up, could end up in somebody's basement and kill a whole slumber party full of kids sometime, all right. It's not the case that a catastrophic event, a Lake Nyos, a 2,000-person event, is very likely. There's a lot of work done on what it would take to get an explosive loss of a large amount of CO2, and it's really hard. You need some big concentrator like a lake that can turn over at once to do it. Go ahead.
Buy something in on a new development built over a CO2 cloud? I mean, I'm not going to buy that.
You're absolutely right about that. So it's the risk to individual homeowners that I think is pivotal. The risk to when the company says, don't worry, we're going to put a CO2 detector in your basement, it doesn't make you feel better, right? However, if you look and ask, well, where are there opportunities where we're already doing EOR in a relatively unpopulated area, in a place with a capped reservoir, for instance, Permian Basin, where there already has been injection of hundreds and hundreds of megatons? Where are there offshore facilities where there are spent oil and gas reservoirs where you can inject CO2 in them, and it's not, in fact, over land at all? The North Sea has something like 60 years' worth of European electrical power generation just in empty North Sea reservoirs. And so if you total up those areas where you really can do the job, the answer, without risking killing the girls in the slumber party, the answer is there's a wedge's worth there. Whether or not there's any more, I don't know. But as we get going with these hydrogen burning power plants, one of the plans that is afoot for something that's coming in the future is to divert a substantial fraction of the stream of CO2 that's coming off and to inject it into all kinds of different facilities with seismic sensing, just as an experiment, so that we learn to manage CO2 below ground. All right? So we can learn as we go, and there's enough for a wedge to get started. And you can also solve this problem with no geologic sequestration. Whether or not you can get the political solution, I don't know.
Okay, well, I need to send Dr. Pacala back out to his car to go to the airport, so we want to give him a big thanks for his presentation.
Thank you all.
You in the audience, please stay. Wade Adams is going to give us a summary of the 2 days that you didn't sit through about batteries and solar and revolutionary changes that could be more than a wedge. And then we're going to have some refreshments in the back, courtesy of the French government. So, Wade?
Thanks, Amy. Well, I think we've had a great 2 days. I know Rick Smalley would have enjoyed it immensely. He's only been gone less than 3 weeks now. And I'll just give you a few summary slides, and I'll intersperse some Rick Smalley pictures as we go through this. Of course, everybody knows that Rick is most famous for his Nobel Prize, the discovery of the carbon-60 molecule. that was one of the three seminal events that really created the nanotechnology revolution. But his work in the last 3.5 years to develop the vision of the distributed storage in-grid, and the amazing thing about Rick was his ability to assimilate all the information that we just heard, the diversity of approaches to solving the energy problems, looking at all the possible ideas that are going to give you wedges of CO2, or as he liked to call it, the terawatt challenge. If you can't bring a terawatt of new clean energy to the table, you don't have a serious plan. And that led to the distributed storage in grid approach, which has been highlighted in many places. And in his game, everybody played. So he did agree with the last talk that you don't have to choose winners, you just have to get going, and we really needed to get going about 10 years ago. Let's go the right way. So Rick Smalley was comfortable with bureaucrats, shown up on the upper left-hand side, and he also liked to have fun. Here he is injecting electrons into an armchair quantum wire model, which is an activity he called supremely silly. And here's what that model of the nanotube looked like here when we built it at Rice last April. It was a 360-meter long nanotube model, done to scale, about 0.7 of a nanometer diameter, equals 14 inches. And the largest nanotubes that have been made today on Earth on this scale would be nearly 20,000 miles long. And so it was a supremely silly event, but it did illustrate how incredibly small nano is and how you have to readjust your thinking if you're going to work in nanotechnology. So what we've learned from this conference, very, very sharply summarized, is that the grid really needs to become more of a business, not a government-regulated business, if faster or any innovation is going to occur in the grid. Smart meters are becoming available and the cost is dropping, and they're now much more cost-effective than they were. Pricing options, regulators aren't keeping up with the research results, and in fact most regulators are not well educated about new technology and their effects. Consumers ought to be part of the pricing structure, and new analysis shows that alternative energies indeed are cost-effective under peak demand pricing. So here's Rick in the Oval Office with President Bush and a bunch of government people over here, a bunch of industrial people over here, and the esteem with which Rick was held by the international nano community as well as the national nano community is that Rick was the only academic invited to the White House for that ceremony as the NNI program was signed into law. Now, unfortunately, Jim Von Air left, but this little white fuzz right in here, let's get it up. Didn't show. Well, anyway, Jim Von Air is hiding right behind this guy right there. And so he chose poorly in where he stood for this picture. So what have we learned in 2 days now about the grid? The grid is old and rapidly aging, but it works amazingly well for what it was designed for. It wasn't planned to carry vast amounts of energy across very long distance, however, and that sets up the opportunity that we have to do better. Energy demands for electricity will surely increase considerably. Technology enablers are advancing, but slowly, with low levels of federal and private funding available for both technical research as well as development. And lastly, there's plenty of money to be made in developing the future grid. So here's Rick Smalley at a very young age with his sister. You can kind of see the sparkle in his eye there about looking to the future. His high school graduation picture. And here's Rick looking pretty grim. That's actually 2 days after he decided to quit smoking. The new grid technology, we saw two prime examples of what could happen. High-temperature superconductors, the first demonstrations are imminent, especially at Con Ed. Economics look promising, but it's taken 40 years to get there. We heard there are no physics limitations to achieving sometime a room-temperature superconductor, and nanotechnology will surely enable improvements to both performance and processability as well as cut the cost down. So here's Rick's central research group, part of the Carbon Nanotechnology Lab. The last group picture that was taken back in 2004, some 35 people there. The total number of people working on carbon nanotechnology now numbers about 60 here at Rice. The other new grid technology is the armchair quantum wire, the carbon nanotube wire, and research is advancing on our processes to make scalable amounts of pure metallic single-walled nanotubes that will be required. The fiber spinning processes, not just at Rice but other places, have been demonstrated at the lab scale and do offer scalable manufacturing processes for the wire. Other killer applications for carbon nanotubes will undoubtedly help advance the technology instead of just relying on the grid application to pull it along. And we have many opportunities for collaborations to accelerate this technology development. In fact, to pull it from the 22-year estimate that we heard, perhaps to as soon as 10 years. And as Rick dubbed with this picture done in the mid-90s, the Carbon Nanotechnology Lab was his answer to what was needed. And as he said, if it ain't tubes, we don't do it. So the Carbon Nano Lab at Rice does tubes. The storage part of the meeting was really amazingly diverse and interesting. All the alternative technologies were looked at, whether it's pumped water or gases or the chemical approaches, synthetic fuels, supercapacitors, batteries, flow cells, flywheels, hybrid systems, especially solar thermal and concentrated photovoltaics look very interesting and attractive. We heard a 10% 1-hour criterion to be applied for the grid. There's a lot of very clever ideas out there, and they must be evaluated against various criteria as a system. We can recognize now the advantages and disadvantages of viewing energy as either heat or work. And we heard that Disney's first law, that is, wishing doesn't make it so, doesn't trump the laws of thermodynamics. So here's Rick with his favorite students, that is, anyone of any age. Rick loved to teach at all levels. Here's a bunch of his favorite students coming by Rice and crawling around on the gymnasium equipment, which we call a carbon-60 molecule in the hallway. Nanotechnology for storage. We need to think about other forms of carbon. Nanotubes are clearly going to be a player. Let's hurry up on their development. And all of the things that we've been talking about for the last 3 years are still very relevant. We need high strength, lightweight, durable coatings, high efficiency catalysts, high temperature resistance. We need to have things smaller, faster, and cheaper. They're all still very good targets for nanotechnology R&D. These are the 2 slides that we came out with after the May 2003 conference. Most of these are still very relevant. I won't go through them in detail, but we did discuss in more detail some of these various aspects of the nanotechnology grand challenges to be met. We came up with 14 of them 2 years ago, and there's still a lot of work to be done. Rick and his wife Debbie, who was here for the first few talks yesterday, played Nano Geeks back in 2004. She's a teacher, and she plans to carry on many of Rick's best tendencies with her students. The bottom picture is Rick looking at the Greek islands a year ago, and I think this shows his visionary image to us clearly. Final thoughts. Can we all work together to initiate what was proposed to be Smalley prizes, much like the X Prize helped get people into space commercially? And we could envision Smalley prizes for solar, grid, and storage milestones to be determined and to be highly rewarded and to accelerate the research and development needed to do these things. Can we maintain the vision of Rick Smalley? I think the answer is yes. We must continue to work together to influence the technology development, the federal government, the industry, and all of the players that we need to work on. It is critical that we continue to do what we've done these 2 days, that we couple the policy, the economics, the entrepreneurial, the technical aspects, rather than all going our separate ways and meeting in our own little pipes. So I want to end with a quote from Robert Curl, his co-Nobel laureate. Bob gave this quote the day that Rick died. Rick was a visionary, and his charisma and logic made those he worked with buy into the vision. Rick convinced us that we could be better, stronger, and take more chances if we just tried. I hope that we don't forget. Then his legacy will make a lasting, transformative difference. And with that, I'll close with Rick's message that he took to many, many audiences over the last 3 years in this area. And that is, be a scientist, or if you prefer, be an engineer, save the world. That's what it's all about. Thank you for coming. Thank you very much.